Hi, this video helps you to learn how to solve traveling salesman problem using branch and bound paradigm. So what is branch and bound paradigm? Before going to see the technique, let's see what is the solution for any problem. So normally when you are given with a problem, there will be some set of constraints attached to it. So if you're finding solution to the problem, we have to check whether that satisfies all the problem's constraints. If the solution satisfies all the problem's constraints, then it is known as feasible solution. Out of all the feasible solutions, some of them may give the best value of the objective function. So that solution is known as optimal solution. For example, if you are taking a traveling salesman problem, a traveling salesman problem is we have to start from all the cities, right? Let us take a set of cities. A traveling salesman have to start from one city, has to visit all the cities, and once again get back to the starting city. Right. So if we can visit all the city and come back to the city, come back to the starting city, then that is making a cycle, right? So that is known as Hamiltonian cycle. And if you are finding a solution for Hamiltonian cycle, then that is an example for feasible solution. But out of that Hamiltonian cycle, if you are finding the shortest Hamiltonian cycle, then that is known as optimal solution. Normally, the one more example we can take, finding the sum of subset of items, and if you are taking the most valuable subset of items that fit the snapshot means, then it is an optimal solution. So branch and bound method is one of the methods to systematically search a solution space. That is, it has to find all the solutions for any of the given problems. So it is similar to backtracking technique, but in backtracking technique we are using depth first search, but here we are going to use breadth first search. That means when you are taking any one of the representations, we will see the representation next. Before that, we will see what are the similarity between backtracking and branch and bound. So in backtracking, we are using bounding function to avoid generating subtrees that do not contain answer node. So here also we are going to use bounding function, but in branch and bound, we are using breadth first or D search or least cost search based on bounding functions, right? And when you are taking this tree organization of the solution space, the tree is known as state space tree is used. So the state space tree is having set of nodes, and when you are traversing from the root node to the leaf node, it will create a set of tuples which represents all the vertices of you have visited, or based on the problems you may have different ones, right? So if from the root node to the leaf node, if you are visiting, you will get set of tuple, a set of values. That complete value set will be making it a solution for that problem. Similarly, each branch will give you one solution. Out of these solutions, some may be an answer node, some may not be an answer node. So in case if you are generating this tree, if you start from the first root tree, and after generating this, you have to find all the children of these nodes, and after generating all the children, then only it will start exploring the next level of the next level nodes. So that is breadth first search technique. In backtracking, we are using depth first search. First it will create one child, and then it will start exploring that child. But here you will generate all the children, then only it will come to the next level. So here, at the time when it is generating this children, this node is known as E node, a live node whose children are currently being explored. But these 2, 3, 4 are generated by this parent, but yet it has to generate their children. So these 2, 3, 4 are known as live node. And if this branch doesn't lead to the answer node, then we are not going to extend this tree, or we are going to prune this tree based on the bounding function given in the problem. So that node is known as dead node. So let's see branch and bound technique in detail. So in branch and bound refers to all state space search methods in which all children of an E node are generated before any other live node can become E node. Now that is clear to you, I think, right? Now there are two graph search strategies we are using here. One is BFS and another one is D search. BFS and D search both are giving same type of strategy, but here BFS will give you variable size type tuple and D search will give you fixed size tuple for the solutions. right? And here BFS will be having first in first out methodology, and it is using Q as a data structure. In D search we are using last in first out, and it is using stack as a data structure. One more search strategy is there, that is known as um, least cost branch and bound search. It uses a cost function to search the node in this state space tree. So for finding the cost function, it is using h of x and g of x. So what is h of x? The cost of reaching the node x from the node root. Okay, and g of x is the additional effort needed to reach the answer node from x. So g of x is what are the additional effort required, and h of x is what is the cost to reach the particular node. So when you sum these costs, that will give you the final cost of reaching that node. So that is known as cost function, which is used in some of these strategies. That strategy is known as least cost strategy, and that LC search coupled with bounding function is known as LC branch and bound search. There are two special cases for least cost search strategy, and one is breadth first search. If g of x is 0, it will consider only h of x, then it is a case of breadth first search. And if h of x is 0, we are not going to check the what is the cost of reaching the particular node. We are just concentrating on the additional effort needed to reach the answer node from x. So that time it is a D search node, and normally this D search node is giving you the final fixed tuple. That means it will have fixed size for all the solution, right? So normally this g of x will be always greater than g of y. Okay, so in this branch and bound paradigm procedure, we are starting from the root node and apply lower bound and upper bound for this, and then if the bounds matches, then an optimal solution has been found and the algorithm is finished, right? If they do not match, then algorithm will run on the next level, that is on the child nodes. Let's see how to solve traveling salesman problem using branch and bound. Before going to see the procedure, we will see this example. Okay, normally in a traveling salesman problem is sales. Hi, here the given matrix is cost matrix, and there is so there are 5 vertices, so 5 rows and 5 columns are there, and if there is no edge from one city to another city, then that is mentioned as infinity. There is no edge for same city, and when you are taking values, if there is no direct edge from one city to another city, that should be mentioned as infinity. But here all these values are non-zero values. That means there is a direct edge from one vertex to all these vertices, right? Similarly from second to all vertices. Now this cost matrix should be reduced into reduced cost matrix. That is the first step. So when you are making this reduced cost matrix, let's see how to create this reduced cost matrix. So first you have to find row wise reduction, then column wise reduction, and find the cumulative reduced sum. So row wise reduction is nothing but for each of these rows you have to find the smallest element and subtract it from the remaining value, subtract that value from the remaining elements. And in this case the first row is having the smallest element 10. Okay, so the first element is first row is having 10 as the smallest element, so we have to reduce all the elements from 10. So 10 is the value to be reduced, and when you are taking the second one, 2 will be reduced, third row 2 will be reduced, and the fourth row 3 will be reduced, and fifth row 4 will be reduced. So the reduced value is 10 plus 2 plus 2 plus 3 plus 4, 21. So after reducing this, what should be the value here? Here this will become 10 and this will become 20, right? And this will become 0 and this will become 1, right? So this is 20 and this is 10. Right? When you are subtracting this value, this becomes 13 and this becomes 14 and this becomes 2 and this becomes 0, right? And similarly the third one, here the reduced value is 2, so this becomes 0, this is 2 and this is 3 and this is 1, and similarly here this becomes 16 and this becomes 3 and this is 15 and this is 0 and this is 12 and this is 0 and this is 3 and this is 12. And now we have to check in each column. In the column wise, we have to check what is this value. 13, this is 12, this is 13, and this is once again this one is 1, right? And this one is 16 and this one is 12. So among these, which is the smallest element? 1 is the smallest element, so 1 should be reduced. And here already we are having 0, so no values will be reduced. Here this value is 3, so 3 is the smallest value, so that should be reduced. Here already this value is 0, so no values will be reduced. And here also this value is this 2 is 0, no, so no value will be reduced here. So the summation is, in the column wise, in the first column 1 is reduced, in the third column 3 is reduced, and the remaining column 0 is reduced. So summation is 4. So the summation of row wise reduction and column wise reduction is 25. So this value is taken as a lower bound and the upper bound is infinity. Now from this node we are going to see which are all the vertices to be visited to get the optimal path. So you have to start from vertex 1, visit all the vertices 2, 3, 4, 5 in any order, and finally it has to come back to 1. So let's see what are the possibilities. So if you are starting from 1, let's see how to reach, what is the cost to reach 1 to 2, right? So if you take 1 to 2, we have calculation of cost is based on the procedure. The procedure is given here. If you are taking the path 1 to 2, the source row should be made as infinity and the destination column should be made as infinity. So we are taking this reduced cost matrix, make the source row 1 as infinity and reduced column as infinity, and the return path 2 to 1 should be made as infinity. So 2 comma 1, that should be made as infinity, right? So this should be made as infinity. So once if you made this as infinity, and after making this, now we have to reduce it. So reduction means we have to do both row wise and as well as column wise. So reduced value for the second row is 0. This is already all are infinity. So this is 0 and this one is 0 and this one is also having 0 values and this one is also having 0 values. Now column wise, this one is 0 and here all are infinity. So this is also having 1 0 value, smallest value, and this is also having smallest value, so nothing will be reduced. This is also having nothing. So if you are taking row wise reduction, sum is 0 for all the rows and for all columns 0. So what is the total cost? Total cost is the reduced cost which is given in the root, that is 25, plus the cost of reaching from this I to j. So I to j is 1 comma 2 is 10. So 10 should be taken, and what is the R value? R value is 0, so 35. Similarly, we have to find for path of 1 comma 3, 1 comma 4 and 1 comma 5. So let's see 1 comma 5 now. So if you take 1 comma 5, of what you have to do is take 1 row as infinity, 5 column as infinity, and 5 comma 1 as infinity. Okay, now reduced matrix. So this one is infinity and here 2 will be reduced. Okay, and here already 0 is there, and here 3 has to be reduced, right? And here already 0 is there, so here 3 has to be reduced, right? Now if you are taking this column, when 2 is reduced, this will become 0, 10. But here already 0 is there, so nothing to be reduced. So 0 is there. This column is also having 0. This column is also having the least value as 0. This column is also having the least value 0. So the total sum is, reduced sum is 5 for row and 0 for column. So the total value is 5. Okay, reduced value is 5. So what is the cost of the node? Node is lower bound value is 25. What is the path of 1 to 5? 1 to 5 is 1 here. So this is the path of 1 to 5, right? So that is 1. So the total value is 31. So 31 is mentioned here. Similarly, we have got 53 for 1 comma 3, and 1 comma 4 is having 25. So after generating all these children, now we have to check which node should be made as a live node. So out of these nodes, we have to choose the smallest value. The smallest value is 25. Now we have to start from this 4. Next, we have to see which are the remaining vertices to be visited. So the remaining vertices are 2, 3 and 5. So let's start with 1 comma 4 comma 2. So if you are taking 1 comma 4 comma 2, this matrix is generated by referring this path 1 comma 4 node, right? So here this is taken as the matrix now. Now we have to check. We are going from 4 to 2. So the source is 4. So fourth row should be made as infinity, and column is 2. So 2 should be made as infinity. What is the returning path? It has to return to 1. So 2 comma 1 should be made as infinity. You should not confuse here. You should not make 2 to 4 as infinity. Here the path should return to 1. So 2 to comma 1 should be made as infinity. Now again reduce it. The first column is already, row is already having all infinity. Second column is having 1 0. Third column is also having 1 0. Fourth row is also having 1 0. Fine. Column wise, this column is having 0. This column is all infinity. This is also having 0. This is also having all infinity, and this also having 1 0. So no values will be reduced in both column wise and row wise. So what is the cost of path of 1 comma 4 comma 2? So what is the cost of this root? So here the root is this one. So what is the cost of this root? 25. So 25 is taken, right? And then what is the cost of 4 comma 2? So 4 comma 2 we have to take. 4 comma 2 is 3, right? So 4 comma 2 is 3 we have taken, and we didn't reduce any value. The value is 0. So the value is 25. So this one is 28. Actually this should be 28. Sorry, I have written wrong. So this should be 28. So this will be having 28. So similarly, 1 comma 4 comma 3 is having the value 50, and 1 comma 4 comma 5 is having the value 36. So we have got these three. Out of these three, smallest one is this one. So this 28 will be taken. Okay. Now in this 28, once again we have to start, right? So 1 comma 4 comma 2 should be taken as the source matrix. Now from this source matrix, you have to choose either to go to the vertex 3 or vertex 5. If you are taking 1 comma 4 comma 2 comma 3, right? So what you have to do is, now the source matrix is 2. So make all row as row values as infinity, and destination is 3, right? So 3 as infinity, and the return path is 3 to 1. So that should be made as infinity. Now see the reduced matrix, all infinity. This is all infinity. This is having 2. So 2 should be reduced, and this is infinity, and this is having 11. So totally 13 will be reduced from the row, right? But column wise, so this is all infinity. As we are reducing 11, this will become 0, right? And this is all infinity. This is already infinity. This is also infinity. Once we are reducing 2, this will become 0, right? So total 1 comma 4 comma 2 comma 3 is 13. 13 is reduced. And what is the cost of 2 comma 3? So 2 comma 3 is 11. So we have to take the path from here, right? So the path value is taken from the matrix A. This is the matrix A. So 28 plus 11 plus 13, 52. So the value is 52. Similarly, path of 1 comma 4 comma 2 comma 5 is 28. So the total value is, among these two, 28 is the smallest. So the optimal solution is, from the 1 we are moving to 4, then 2, then 5, then 3, right? So 1 comma 4 comma 2 comma 5 comma 3, and once again come back to 1. So when you are taking 1 comma 4, now we have to refer the cost matrix. 1 comma 4 is 10. Okay, from the 4 we are going to 2. So 4 comma 2 we have to take. 4 comma 2 is 6. From 2 we are going to 5. So 5 is 2 to 5 is 2, right? And from 5 to we are going to 3. So 5 to 3 is 7. So from 3 to 1 we are going. So it is 3. So the total value is 28, right? And the worst, so here we have easily generated the solution node, which is the optimal solution. And in the worst case, we are generating node for all these nodes, right? We are generating in nodes for all the other nodes. So the total complexity is order of n square into 2 to the power n. So let's see this procedure. So first you have to find the cost matrix for the given graph, and we have to find the reduced cost matrix. In the reduced cost matrix, first you have to find the row reduction and then column reduction, and find the sum of these values reduced in both row wise as well as column wise. That cumulative reduced sum should be taken as lower bound and infinity should be taken as upper bound. Now we have to find the path for each, that means you have to find the cost for generating each of the live nodes or each of the children. So for that you have to take the root node lower bound value, and you have to make all the that is that matrix will be taken as the vertex will be taken as the source matrix vertex, and the destination vertex will be S, and the cost of R2S is taken as by making all the row of R should be infinity, all the column of S should be infinity, and also we have to make the return path, the last node to the first node, j to 1 should be made as infinity, and then we have to reduce row and columns, and find we have what is R value, right? The summation of these two, right? And then the cost of that matrix, the live node or cost of S is the cost of the root plus the path value from y to j plus the reduced value, right? Similarly, we have to find for all children, and out of that all children we have to take the lowest value, and once again we have to choose that path and proceed it further until we have all the nodes are visited. So this is the algorithm for traveling salesman problem. Thank you so much. The complexity is order of n square to the power n.